Okay, Santosh, you're streaming now. Good, thanks. So again, let's start then. Welcome to everybody for our Thursday colloquium. We are now doing this twice a month, graduating from every week, as we had at the beginning of the lockdown period. And we are so addicted to this now that we haven't gone back to in-person seminars. And this also gives us the great privilege of inviting people to give our colloquia without physically flying them over, which is always a good thing to do, but sometimes this is easier. So there you are. We are very much privileged to have Professor Carlo Berenghi from University of Newcastle University, Professor of Fluid Dynamics there, went to the University of Milan, and then I think your PhD was at the University of Oregon, and then has been Professor of Fluid Dynamics at Newcastle for a long time. And today's topic is extremely interesting and has potentially many cases that we can encounter in astrophysics. So let's hear about quantum turbulence. Go ahead.
Thank you. Thank you for inviting me. Let me share my slides with you. So today I'm going to talk about quantum turbulence. And first, let me mention people with whom I've been working on this problem. So I want to mention in particular Luca Galantucci, Andrew Bagley, Nick Poukakis, Nick Parker, and Yuri Sergeev here at Newcastle. I put actually a map of Britain on this slide just to show you where Newcastle is. So I'm in northern England at the boundary with Scotland on the River Tyne. And the name Newcastle comes about because of the new castle built by the Normans in 1080 to replace the previous Roman fort. But actually, this work has been done very much in collaboration with people in other places too. At the moment, in particular, I want to mention Giorgio Krustulovic in France and Ladix Skrbek in the Czech Republic, Ferrari in Italy, Vandele Bagnato in Brazil, and Srinivasan in New York. So my aim is to give you an idea about quantum turbulence, explaining what is similar and what is different when we compare quantum turbulence and ordinary turbulence. So the outline is quite simple. I'm going to tell you about the basic physics, which is Bose-Einstein condensation. Then I'll tell you about quantum vortices and the turbulence of quantum vortices. So let me start with the fundamentals. So we need to consider systems which are quantum and very cold. So we know from quantum mechanics, from basic quantum mechanics, that an atom with a mass m and a velocity v has a de Broglie wavelength associated. We also know from statistical mechanics that if we take a box with a gas of atoms, the temperature is defined as the average kinetic energy. So using this formula, we can then relate somehow the de Broglie wavelength to the temperature. And we find that actually, as you can see, that the de Broglie wavelength scales like the temperature to the power minus 1/2. So that immediately raises the question, what happens if the temperature is reduced towards absolute zero? Indeed, this field of quantum turbulence is very much associated to progress in low temperature physics. Now, this question of what happens near absolute zero becomes crucial for bosons, particles with integer spin, because unlike fermions, which have half integer spin, they're not prevented by Pauli's principle to pile up and occupy the same energy state. So you see in these schematic diagrams that whereas fermions will actually spread over available energy levels, bosons can collapse down at the bottom on the lowest energy level. And I want to also mention that this implication were actually worked out very much in detail for an ideal gas by Bose and Einstein as early as 1924. They came up with this idea of Bose-Einstein condensation, which I'm going to describe, at least in the case of an ideal gas. So let's consider now what happens to the de Broglie wavelengths compared to the typical distance between the atoms of the gas. As I said, as we reduce the temperature, the de Broglie wavelength increases. So let's start at the left-hand side. You see that schematically, we see a box containing a gas, all the atoms moving at some velocity, and we are at very high temperature. And essentially, we have a ballistic gas. But as we reduce the temperature towards zero, the wavelength of these essentially wave packets will become noticeable on the scale of the distance between the atoms. And at some critical temperature, and that is why we define the critical temperature, the de Broglie wavelength will be of the same order as the distance between the atoms. So at that point, you cannot really tell that you have individual atoms any longer. You're simply left with some kind of overlapping waves, and a lower temperature, essentially a single gigantic quantum wave. And that is actually the wave of representing a Bose-Einstein condensate. So this is the basic, the simplest way to think of a condensate as the quantum mechanical wave description of matter, which takes over, but a stress over a system which is macroscopic. So we have a wave function ruling a macroscopic system. Now, this was actually conceived as an idea in 1924-25. It was actually realized experimentally in the laboratory only in 1995, much later. And you see here at the right-hand side at the bottom, an experimental diagram showing the number of particles which have collapsed into this gigantic microscopic ground state wave function. You see, starting from the right of the graph at high temperature, as T divided by Tc, the critical temperature is lower below 1, we see an increase of numbers of particles in this quantum ground state. However, actually, much before 1995, it was already known that something strange which was related to that was going on. As early as 1938, a physicist called Kapitsa discovered the superfluity of liquid helium. He found that the effect appears when the temperature is lower below 2.2 Kelvin. So he called this phenomenon superfluidity in analogy to superconductivity. Superconductivity is the motion of electrons, of charges, without suffering any electrical resistance. And superfluidity is the motion of a fluid without suffering viscous effects. Now, in the same journal, in the same issue, or in the same number of the journal, which was Nature, Fritz Landon and other physicists argued that the strange properties of liquid helium are related to Bose-Einstein condensation, which at that time was known only for ideal gases. And there are lots of strange properties of liquid helium, and the most apparent is this one, represented in these images. If we take a container made of glass so we can see the liquid helium and we cool it, you see on the left that at temperatures above the critical temperature, the liquid helium is boiling very violently as we lower the pressure by pumping the vapor above the liquid. Essentially, it boils. But as soon as we cross the critical temperature at Tc, the boiling suddenly stops. And it suddenly stops because we go into this quantum phase of liquid helium, where it becomes essentially a perfect heat conductor. So that something was going on in liquid helium was known, as I said, already in the 30s. This connection between Bose-Einstein condensation and superfluidity, however, is a bit subtle, and we'll tell you more in a bit. So at this point, it's worth also going back to the idea that as we decrease the temperature, the fraction of the number of atoms in the condensate increases. Indeed, liquid helium can be seen as a mixture of two independent interpenetrating fluids, which we call the superfluid and the normal fluid. The superfluid is inviscid, it has zero viscosity, and its origin is the quantum ground state. It is not exactly the quantum ground state, but it is related to the quantum ground state. The normal fluid is viscous. It's called normal because it behaves like an ordinary fluid. So it is viscous, and it has entropy, and consists of thermal excitations. So the fraction of normal fluid and superfluid depend on temperature. And this table shows that each fluid component has its own density field and velocity field, which for simplicity I represent with symbols Vn and Vs for N for normal, S for super. And the table also shows that it's only the normal fluid which carries viscosity and entropy. The bottom figures show the relative proportion of superfluid and normal fluid. So the normal fluid density, you see, is 1 at the critical temperature and then drops quickly. Vice versa, the superfluid density is 0 at the critical temperature, and as we lower the temperature, it rises quickly and it becomes 1 essentially at a temperature below 2 Kelvin. So it does not take actually a big effort from the point of view of low temperature techniques to cool liquid helium and make it to become an almost perfect superfluid. So this is the system which we consider. And why is it superfluid? Actually, superfluidity and Bozenstein condensation are not directly related. Superfluidity, as shown by Landau in the 1940s, follows from the particular energy-momentum relation, the dispersion relation of the elementary excitations. So if you take an object which moves inside our condensate, it will not be able to lose energy unless it moves faster than the critical velocity. And that follows from simple considerations of conservation of energy and momentum. So imagine we have an object, which is the red ball represented in the figure at the right, moving at velocity v1, at some point creating an excitation, therefore losing energy, and the excitation is represented as a wiggle here, a wave of momentum k. The object then acquires a velocity v2, changing both energy and momentum while conserving the total energy and momentum. And that is the simple-minded approach taken by Landau to show the existence of the critical velocity. For a particular dispersion relation, then we can work out whether this critical velocity is 0 or not. It turns out for liquid helium it's not 0, it's quite high. And you see on the left a diagram showing the drag force on a small object. Technically it is a little bubble created by an electron by its 0-point motion inside liquid helium. So the drag force is plotted versus the velocity. There are actually two curves on this graph. On the left, there is a very sharp rise of the drag for the bubble moving in liquid helium above the critical temperature, indicating a very large drag, the drag of a small object at the Stokes law, essentially. And at the right, you see that unless the critical velocity exceeds a critical value, which is about 50 meters per second, there is no drag. So we have superfluidity. So the mechanism to create superfluidity is different. In any case, what really makes superfluid helium and other condensates, which one can show are superfluids too, interesting, is not only superfluidity, the lack of viscosity, but also something else, the existence of quantized vorticity. And these, So this is a property which follows from having a macroscopic wave function psi. So let's represent psi, which is a complex field, in terms of its magnitude, which I write as the square root of a number density, and phase, which is the exponent of the exponential.
Kalu, we can't see your slide.
All right. Let me.
Now we can see it.
Yeah, let me go back. I hope.
Yes, yes. Now it's fine.
So we see that from this, using some simple quantum mechanics, it follows that we can define a velocity, which is proportional to the gradient of the phase, and also a number density, which is essentially the square of the wave function. So far, so good. But really, what makes the system interesting is the circulation. Now, consider the circulation integral of the velocity around some closed paths. Then you can show that if there is a phase defect inside the path, that is to say a point where the wave function is equal to 0, then this circulation must be an integer multiple of what is called the quantum of circulation, the ratio of Planck's constant and the mass of the atom. And if there is not any phase defect, then the circulation is equal to 0. We have purely a rotational flow. Now, the spontaneous formation of phase defects can take place. What is a phase defect? A phase defect is a vortex, is a point in two dimensions or a line in three-dimensional space where the wave function is 0, exactly 0 on the axis of this vortex, and therefore the phase, which is the arctangent of the ratio of the imaginary part and the real part, is not defined. So that's why we call it a phase defect. So a quantum vortex, therefore, is nothing but a hole in the density, like a bathtub vortex, around which there is a circulation which comes in multiples of 2 pi. So the bottom figures describe schematically this concept of the vortex. You see on the left, you see the density hole. So the wave function drops quickly towards 0 at some location. And actually, this decay takes place over a typical length scales, which we call it the healing length, psi. And around the phase defect, which is represented in the middle figure, the phase changing from 0 to 2 pi, there is a flow corresponding to this varying phase. So we have a flow, the varying phase, around this singularity. The consequence is that the velocity is simply of the form kappa, the quantum of circulation, divided by 2 pi r in the azimuthal direction. So we have reproduced in the physical world the very simple idea of the vortex line of the textbooks of elementary fluid dynamics. So in other words, we have a quantum vortex. And so it's important actually to distinguish a quantum vortex from any kind of classical vortex, like the vortex which you can create in a cup of coffee with a spoon. In the ordinary vortex, the fluid is viscous. In our quantum vortex, the fluid is a superfluid, so it will spin forever. You don't need, if you remove the spoon, the coffee spins forever. Also, the strength of this vortex is fixed. One can show that multiply charged vortices carry more than one quantum of circulation, in most situations become unstable and break up into singly charged vortices. So the velocity field is completely constrained by this form, V equal kappa divided by 2 pi r, around what is essentially a very, very thin vortex line, because the healing length is actually a very small number in any system. In liquid helium, it's about 1 angstrom. So the size, that is about the size of an atom. You may say, oh, well, so are you trying to tell me that you have a fluid at this kind of length scales? Yes, that's the reality, because the very idea of atoms here has lost somehow its meaning. If you think of billiard balls, we have essentially some kind of more continuous entity described by wave function, which behaves like this. So this is the simple idea of a quantum vortex. And something else to notice. The velocity field 1 over r contains 0 vorticity, which means, in other words, the vorticity is a delta function on the axis. So, whereas in the classical ordinary vortex, the vortex in the cup of coffee, the vorticity will be distributed. There will be a region, the core, which contains constant vorticity, and then it will drop smoothly to 0. Now, where do you find quantum vortices? Well, there are now many quantum fluids which are known. So most results I'm going to tell you will refer to superfluid helium, the common isotope called helium-4. There is also a rare expensive isotope called helium-3, which is fermionic in character. So it becomes a superfluid almost like, in a sense, like superconductors do. And it's different because it requires completely different technologies. The typical critical temperature is of the order of the millikelvin rather than the Kelvin. So this is 3 factors, 3 decades in temperature approaching 0 is quite a challenge. And then I'm going to tell you about other systems, the ultra-cold atomic gases. These are very rarefied gases. And here I made a list of various species which have been used, starting from rubidium and sodium, etc. Essentially, very rarefied clouds of atoms which approach this limiting description of Bose and Einstein in their famous 1924 paper. And then people are also experimenting with double condensers. Essentially, they mix the atoms and they produce 2 penetrating superfluids. There are also polaritons. Those are actually room temperature superfluid consisting of photons which acquire a mass because of the way they interact with excitons inside a 2-dimensional cavity. There are spinel condensates. There are quantum ferrofluids. There are also, it is thought, neutron stars in their interior. They should be superfluid, although the critical temperature in this case is immensely high. And there are also models of the early universe called axions, which are interpreted as superfluids. So in the rest of what I'm going to tell you, I'll concentrate on helium, and I'll tell you a bit about atomic gases, because those are the systems for which we have more information about turbulence. So how do we create this turbulence of quantum fluids with quantum vortices? It's quite simple. We just shake it a bit. And here there are some pictures to show how you can make liquid helium turbulence. So at the left, you see essentially a superfluid wind tunnel called 2P in Grenoble. It's a long channel, which you see represented in the sketch. There is some kind of propeller which drives the flow along the channel and recirculates it around so as that it comes back. So it's a kind of tiny wind tunnel working at temperatures near absolute 0. Then from the left, there is another image. The 2 central images refer to a machine called Shrek, which is also in Grenoble. This is a setup in which we have 2 counter-rotating disks, essentially 2 blades rotating in opposite direction, producing the classical von Karman flow, well known to people who study magnetic dynamos, for example, the Karadash dynamo. It's a very large system, as you can tell from the photograph. The size of the blades are, I think, 80 centimeters. So put together, the apparatus is quite immense, as you can see, and requires an immense cooling power if you want to keep this cold at temperatures which can be as low as ½ degree Kelvin. At the right-hand side, you see much smaller devices. At the top, there is some kind of tennis racket. It's a mesh. The size is a few millimeters, and it is used to produce turbulence in helium-3. So the mesh simply vibrates and creates turbulence like it would in any kind of fluid. And at the bottom right, there is a vibrating fork. It's the kind of fork which you find inside your pocket, inside your watches. They oscillate, setting the frequency of the watch, of the clock, and they are actually quite convenient. They've been used in many labs to create turbulence. So these are very simple setup. What about atomic condensers? These are clouds of atoms, as I said, very rarefied, confined by suitable potentials, and they can be put into turbulent motion, we think, in various ways. One way is using, for example, the technique of shaking the trap. So I've taken these images from some papers, experiments done in Brazil and in Cambridge. In Brazil, they like to shake the trap. They move it, there is an oscillation back and forth with superimposed another motion in the transverse direction, so it's some kind of shaking. In Cambridge, they trapped this condensate in box traps, so the density inside is uniform rather than harmonic, and it's simply oscillated, and that seems to produce turbulence. Now, in this system, it's quite easy to create two-dimensional turbulence. Essentially, the confining potentials can squeeze the condensate, the cloud of atoms, in one direction, creating essentially a very flat disk. And being inviscid, without viscosity, having no boundaries, it is a perfect two-dimensional superfluid. And you can see what you can do there. You can actually use a laser spoon, that is the expression which has been used, represented by these blue double cones. Essentially, the spoon is moved within your condensate. You stir it literally like the coffee in the cup. And turbulence can be produced also in other ways, which I don't want to mention. People have been able to imprint vortices by essentially creating the phase differences using exterior means. And also simply the cooling the system across the critical temperature, the thermal quench, will leave lots of phase defects, which are vortices, as represented in this picture here. This is an experiment done in Trento. So what does the turbulence look like? Well, I cannot show you experimental images because they are more difficult to interpret. I'm showing you some numerical images from papers we have written in Newcastle. So at the left-hand side, you see a turbulent atomic condensates. You see some kind of small cloud of atoms, and I've plotted essentially a surface representing the density in pale blue here. You see that it is wobbling here. This is a snapshot. There are large waves inside, within the condensate, density waves, and also surface waves. And within this turbulence, within this bubble, this cloud, you see these purple lines. These are the cores of the vortices. They are the regions around the axis where the density is depleted. So around these lines, there is a velocity field which moves like kappa divided by 2 pi r, like in the textbooks of fluid dynamics, and it's very disorganized, and it's quite turbulent indeed if you actually try to reconstruct the velocity field from the vorticity, even with few vortices, as you can see. At the right-hand side, you see the typical numerical simulation, which we're very confident describes the experiments in superfluid helium. So this is done typically in a periodic box. We have vortex lines, which are represented as filaments of concentrated vorticity, which move with the classical Biot-Savart law. Now, in all cases, the vortices actually interact with each other by the 1/r velocity field. So we have turbulence, but also reconnect. When vortices collide, they can actually do a cut and paste job. They can achieve, they can produce a vortex reconnection, which changes suddenly the topology of the flow. And I think it's quite relevant to essentially the entire turbulence phenomena. So this is how we represent turbulence in our imagination, and the experimental images which can be produced are consistent with these numerical images which come from models. The left image is produced by solving the nonlinear Gross-Pitarski equation, which is some kind of cubic nonlinear Schrödinger equation. We are very confident about that this equation describes atomic condensates well. And the right-hand side essentially follows from the classical Biot-Savart law plus a reconnection algorithm. Now, I'm going next to tell you about the turbulence in these systems, and I want to use as a reference the ordinary turbulence we are more familiar with. So I need actually to summarize in a slide what is ordinary turbulence. So I'm using the so-called K41 description, turbulence in the simplest realization, which is statistical steady state. It is homogeneous. It is isotropic. So we maintain it against dissipation by providing energy which is injected at some large length scale, say D, capital D, and essentially injecting very large vortices which are unstable and break up into smaller vortices, but do not lose of the total energy. Energy is simply transferred from large vortices to smaller vortices, following this energy cascade, it is called, until when the vortices are small enough, then viscosity effects can destroy the kinetic energy and turn it into heat. So this is what is represented in this slide. You see a formula above for the total kinetic energy, the integral of the velocity squared. It's divided by the volume so as to produce the total kinetic energy per unit mass. And it's also represented as a distribution, E hat, which is called the energy spectrum, as a function of the wave number. The wave number is the inverse length scale, essentially inverse eddy size. And the important result here, which I'm going to use, is the so-called Kolmogorov 5/3 law. The simple result that the energy spectrum scales as the energy dissipation rate to the power 2/3 and the wave number to the power -5/3 across this range of length scales, from the large length scales to the small length scale. And then there is a dimensionless constant, which is typically over order 1. So this is the simple scenario of ordinary turbulence maintained in this statistical homogeneous isotropic steady state. So the question is whether turbulence in a quantum fluid is similar or not. So what is the answer? Well, first of all, let's consider actually what's the typical systems which we have to deal with. So let me introduce symbols here. Capital D is the system size, the size of the apparatus, for example, the system. For classical turbulence, I'm going to use eta as the Kolmogorov dissipation length scale. Essentially, that is the size of the smallest eddy. Eddies which are smaller than eta, they quickly vanish because of viscous dissipation. For quantum turbulence, I have other two length scales, delta, which is the average distance between the vortex lines. The vortex lines will have clearly a spread of distances between them. There will be reconnection events when delta goes to 0, but they are simply isolated single events which happen now and then. But you can define an average distance between the lines, delta. And finally, there is the vortex core size, which is the small region of depleted density around the vortex core, which is very, very tiny. So in classical turbulence, I take, for example, one of the early experiments which verified the turbulence, the Kolmogorov 5/3 law. We can see that the ratio between the large length scale, D, and the Kolmogorov length scale, eta, is 10 to the 6. It's a huge ratio. Essentially, it's a linear measure of the eddies which you can have. Now, if you take in atomic condensates, for example, this experiment by Hen and others done in Brazil, which you see actually represented at the right-hand side, you see like a cloud of atoms represented by the violet. The density is the cloud of atoms. It has the shape of a cigar. It's very irregular because it's being shaken. And the vortex lines, which you see, are the red lines inside. I mean, this is the result of essentially a direct numerical simulation of the experiment. Then you can get the idea that the size of the system actually is not much bigger than the healing length, which is the size of the individual vortices. There is only perhaps a factor of 100 at the best. And in terms of the vortex separation, well, the size of the system is only perhaps at the best 10 times the vortex separation. So we are clearly in a very different regime. There are not many vortices, essentially. The turbulence is very non-homogeneous, and there are not many vortices. Now, if you look at an experiment with helium, for example, SHREC, which is the largest, and it's running at the moment, we see that the ratio between D and Xi, which is the size of a vortex, is even bigger than in Grant's classical experiment. It's not 10 to the 6, it's even 10 to the 10. So the turbulence is really terrifying in kind of, if you think of these numbers. So it's very much different than atomic condensates. So for atomic condensates, we have something which some people would say, well, can we really speak of turbulence? Because essentially there is not much K-space available. The systems are very small. Still, they're actually quite turbulent. If you look at them, you see already the appearance over very limited K-space. You see the appearance of some kind of scaling laws with a bit of guessing, of course. And you see these scaling laws very clearly with liquid helium. So atomic condensates possibly are the best places where you can look for somehow a crossover from chaos to turbulence. And if you really want really turbulent flows, you should not use classical fluids. You should use helium. Now, but this is not an entire story, because it's clear nowadays from the numerics and from the theory and from the experiments that in liquid helium, at least, there are somehow two kinds of turbulence which have been seen. One I shall refer to as the Kolmogorov turbulence, which is similar to ordinary turbulence. And the second, I'll call it Wiener turbulence, and it's quite different. I'm going to describe it. And these names and other names have been used. I like to use these names, which were introduced by Grisha Volovic some years ago. And actually, he made in his paper, actually, first in a talk, then in a paper, these interesting sketches of what it should look like. So he represented Kolmogorov turbulence as kind of irregular, chaotic bundles of vortex lines, and Wiener turbulence as random kind of vortex loops. And he was indeed on the right track. So how do we distinguish these two turbulent flows? As I said, what we call turbulent flow, what we call Kolmogorov quantum turbulence, looks like classical turbulence. We see the signs of an energy cascade. We see the K minus 5/3 energy spectrum. We also can derive that as a consequence of this energy spectrum for quantum turbulence, the decay of the vortex lengths, if we suspend the forcing, scales like the power -3/2 of the time. So that vortex length scales like T to the minus 1.5. Now, Wiener turbulence is quite unlike this. It looks like a random flow. If we measure in the numerics, if we measure the correlation we find that actually the correlation is lost very quickly, it decays very rapidly. There is no inertial range. There is no sign of a Kolmogorov energy spectrum. And when it decays, because we stop forcing it, it decays slower. L goes like 1/T. So let me illustrate, for example, the Kolmogorov turbulence, Kolmogorov quantum turbulence. So typically either in the experiments or in the numerics, we proceed in this way. We inject, for example, vortex rings at some rate. Essentially, we do some forcing at some large length scales, and we see that the turbulence builds up, the energy spectrum builds up, and from the injection wave number, essentially the transfer of energy to shorter length scale produces the classical inertial range. We see the emergence of the -5/3 spectrum very well in the numerics and the experiments. However, this is only true up to the wave number, which corresponds to the intervortex distance. Because if you look at what happens at larger wave numbers, then the spectrum changes, it becomes slower, it tends to a spectrum which goes like K to -1. That is the spectrum of an individual vortex line when you have a single line. And that is because essentially we're looking at scales such as we only see the closest vortex lines and the rest is essentially hidden. So we have a quasi-classical regime with the -5/3 law up to a point, and then we have some kind of different behavior where we see the quantization of the vorticity. We see individual vortex lines. We can call this regime at the right of this figure the quantum length scales. And I show some experimental figures here. the first experiment, which saw this beautiful 5/3 spectrum liquid helium done in Paris. You see the picture on the left, and that was done in a small box with a propeller which agitated liquid helium. The size was about 12 centimeters. And at the right-hand side, you see the superfluid wind tunnel 2P producing a beautiful -5/3 spectrum in Grenoble. Of course, it's better, even better, because the technology has been improved. Of course, there is quite a, there are more than 10 years from the first experiment to the last, which you see here. And I want to add that the same Kolmogorov spectrum has also been seen in helium-3, the fermionic superfluid. And there is plenty of indirect evidence of Kolmogorov turbulence obtained by looking at the decay of the turbulence, not the sustained turbulence. This is the results of numerics. Even small vortex tangles, we call them vortex tangles. In a periodic box, we create a self-sustained system of vortices, either at finite temperature or in the zero temperature limit. And we see this neat distinction. We see the Kolmogorov regime where we expected, essentially at the classical length scales, and the K-1 regime at larger wave numbers. But the important point here is to understand why we form this Kolmogorov regime only in a range of length scales. And I think we understand this from this kind of calculation. So what you see here in this picture is a periodic box calculation where we have sustained turbulence, and the vortex lines have been color-coded according to the local vorticity, the coarse-grained vorticity, which we could put together numerically by averaging over many vortices. So in yellow, we see regions where the vortex lines are essentially polarized. Essentially, they are oriented in the same direction, and they build up regions where the vorticity, the coarse-grained vorticity, is large. In red, you see vortex lines corresponding to unpolarized vortex lines. And in the cartoon at the right-hand side, you see why we can produce an energy spectrum which looks like classical turbulence. If you have a bundle of vortices which are oriented in the same direction, the velocity field adds up. So you create a region of large velocity, therefore large energy. Whereas if the vortices are essentially randomly oriented with respect to each other, the velocity field actually cancel out, and you do not create any kind of large-scale flow. And this cartoon is actually beautifully represented, can be obtained numerically in a realistic numerical simulation, of which we can actually measure the energy spectrum. And we see indeed that the polarized vortex lines create the K-5/3 energy spectrum of Kolmogorov. And the unpolarized lines create the -1 spectrum. So the total effect combining polarized and unpolarized vortices is dominated by the polarized lines. Although actually in terms of total length, most of the length is in the unpolarized lines. In other words, it's enough to have a small partial polarization of vortex lines. Sometimes you cannot even see it with your eyes. You need to compute it numerically, and you produce the Kolmogorov energy spectrum. So partial polarization means essentially some kind of effective bundles which are present within the disorder of the vortex lines. The unpolarized lines actually are most of the vortex lines, and they contribute to the dissipation rather than the energy spectrum. So this is the reason of the appearance of the classical spectrum. But there's also the violent turbulence, which is, as I said, quite different. And you see an example here from numerical simulations, which agree very well with experimental data. You see that the energy does not peak at the left-hand side. So most of the energy is actually at some kind of mesoscale length scales. You see there is a peak. And there is no build-up of the Kolmogorov law at all. And that is obtained when the forcing is weak enough. And actually, there is quite a list of experiments or numerical experiments in which this kind of turbulence has been produced either in a steady state or as a decaying transient. So it ranges from helium-3 to helium-4 experiments, simulation of essentially heat transfer in liquid helium at small heat fluxes, simulation of the thermal quench of a Bose gas. I'm going to spend a few moments with that. Turbulence in atomic BECs. Here, the range of wave numbers available is small, and there is no way of creating a Kolmogorov spectrum. And even simulations of dark matter in the early universe show a spectrum which has been clearly identified by the authors as a Winan energy spectrum. So let me tell you about the quench of a Bose gas, which is quite an interesting exercise. So this is how a superfluid is created. You take a Bose gas and you cool it. So it's like the problem of creating a crystal, which all students, school pupils do typically. Depending on whether you cool it, you form a crystal slowly or fast, you get different things. So typically you cross the phase transition. So you have in the numerics, you try to simulate this reality by having a uniform occupation number for all the states and a random phase, and let the interactions to switch on. And that is what you see in the top figure from the rectangle, which is the uniform occupation number, and then you see the build up, the pile up of densities at small wave numbers. That is simply the creation of a superfluid. There is quite a shoulder which forms in this distribution, so you create like a superfluid and a thermal fraction in the tail of the distribution. The bottom line shows essentially the superfluid density at different temperatures, which builds up. Now, when you do this, however, there are clearly phase defects, because like the crystal, which cannot form perfectly everywhere at the same time, there are phase defects which are represented by vortex lines, and they are visible here. Indeed, if you actually plot the density, you see vortices very clearly. You monitor them, you can monitor their phase and their decay. So you see in this time sequence a very intense tangle of vortices in a cubic box. The vortices are indicated by these red lines, and the left picture is so dense that you cannot distinguish them. Then vortices start decaying, and you have essentially the turbulence which decays, and then there are only a few lines left. And you can see here, indeed, that the energy spectrum is never of the Kolmogorov form, simply because there is, in this case, there is no forcing at length scale, and you created a pure, beautiful Winan turbulence, which decays exactly as expected, which has a very short correlation function, of course. Right, so we have these two forms of turbulence, which we have identified, which seem to be quite different, but there's something else too. If you go to very low temperatures, then there is no damping, because there is no residual thermal excitations which can damp out the motion of vortices. So you have essentially a pure system, and the vortices become very wiggly. Vortices tend to excite Kelvin waves, which are simply oscillations of the vortex axis. And as these waves rotate, they radiate sound. At the right-hand side, you see a picture of the sound pattern, the density profile pattern created by two rotating vortex lines, for example. So if you have a line which is wiggly, typically at very low temperature, it keeps rotating and it radiates sound. But there is an effect which was actually suggested by Boris Fistonov in 1995, which started an interesting industry. He realized that actually these Kelvin waves, if they are nonlinear, they can actually generate shorter Kelvin waves. So we can actually have a process of a cascade in the same way as large eddies break up and create smaller eddies, and we have the Richardson-Kolmogorov cascade of ordinary turbulence. Here, we can have long Kelvin waves which create shorter Kelvin waves without losing energy, and then more shorter and shorter Kelvin waves until actually they rotate so rapidly then that phonons are excited, and essentially dissipation kicks in the form of acoustic radiation. So we have a cascade process, and the details have been worked out. There is about, for example, the prediction of the energy spectrum. And at the moment, we know the best result is a theory of Lvov and Nazarenko, which predicts the spectrum, and it has been verified very well by the numerics. And you see what is the overall effect in a sample of quantum turbulence. So you see the energy spectrum here. So this is a calculation by Brachet and collaborators. It's a large Gross-Pitesky calculation in which you see actually the classical Kolmogorov energy spectrum at the left-hand side with a minus 5/3 power law. And then at the right-hand side, at extremely large wave numbers, you see the formation of a second energy spectrum, which by accident really happens to have the same power law minus 5/3. And in between, there is a kind of flat plateau, some kind of bottleneck between this Kolmogorov cascade, Kolmogorov-Richardson cascade of eddies at the left, and Kelvin wave cascades of waves from individual vortices on the right-hand side. So this is what we think is actually quantum turbulence in the absence of significant dissipation, a system which has a double cascade. Now, sorry, how am I going with time?
We have about 5 minutes or so.
Yeah, I just want to say a few words to finish about vortex reconnections, because the more actually you study this phenomenon, the more you realize that vortex reconnection are the key of everything. In fact, vortex reconnection are necessary to create any kind of non-trivial flow, starting from some very, very slow potential flow. Now, the idea of reconnections of quantum vortices was the idea of Richard Feynman in an article in a book in the 1950s, when there was no evidence whatsoever. He just thought of that. He thought of vortex lines colliding, splitting, and reconnecting. But now we know a bit about that from numerics, from theory, and from experiments. And the physical significance is actually something which is being worked out. First of all, we know that it's important because there is energy associated with the reconnections. You see, for example, in the bottom figures, two anti-parallel vortices. You see these blue tubes which are approaching each other. As I said, this is like a vortex-anti-vortex pair in a periodic box. They're slightly curved. They're reconnecting. You see the reconnection taking place, cutting and paste, and the two vortex lines separate after the reconnection. And at the right-hand side, you see on the plane where the reconnection has taken place, you see actual the density perturbation which has been created. You see like a sound pulse which has been ejected, created by the reconnection. So there is an energy loss associated with reconnection. To reconnect vortex lines, therefore, requires to do some work. And if you actually disconnect vortex lines, you release some energy into the system in the form of sound, which is phonons, which is heat. So somehow the process has to do with dissipation. Reconnections have also been seen individually in quantum fluids. The images at the top show two vortex lines which reconnect in liquid helium. Here, the vortex lines have been visualized using micron-size tracers, essentially tiny solid hydrogen snowballs which are trapped inside the vortices. And as the vortices come together and they do the cut and paste and job and then they separate, the images can be taken using a laser. So this is a real-life sequence of an individual vortex reconnection. And similar reconnections have been observed. It's actually more difficult to do it in Bose-Einstein condensers in an atomic gas. You see some images of vortices reconnecting taken at the University of Trento in Italy. Now, recently we've been working on reconnections in Newcastle with a group in Trento, and actually we came up with we found that there is some universal scaling behavior of reconnections. Essentially, there are two possible power laws for the minimum distance between the vortices, which are called delta. That changes with time as the vortices approach each other and then they separate. So there are really two regimes, one in which delta scales like the square root of time, and one in which it scales like time. Now, the second regime appears when there is either a density gradient which drives the vortices towards each other, or there is a characteristic velocity of the vortex line induced by essentially the curvature. So, for example, if you have a vortex line which is straight, which is hit by a vortex ring which travels fast and splits it, then you will get this, by dimensional analysis, you can get this scaling law, which we verified in a great number of simulations using various models. And then there is the square root regime. This is the regime of interaction. For example, if you take two anti-parallel vortices, sorry, if you take, two orthogonal vortices would be the best, actually. Two orthogonal vortices which are close to each other, which cut and paste, you would see this regime. And also this regime kicks in when the vortices are very close. So you see in this diagram on the right-hand side, the square root law on the red line extending at very small separation delta. That is the regime where actually the vortex cores start merging. The depleted region densities around the axis of the vortices, the phase singularities, start merging, which essentially reduces the nonlinearity of the nonlinear Schrödinger equation, which rules the condensate. It becomes a linear Schrödinger equation, and then you get this scaling law. So I want to stress that because of these results, actually, there have been some recent numerical simulation of Navier-Stokes done by Hussain and collaborators in America, and they actually reproduced. They found both scaling laws for the two different kinds of reconnections. So you just need to take essentially Navier-Stokes vortices, essentially vortex tubes, which are rather kind of thin, so the vorticity is concentrated, and then you get this behavior. So this is truly some kind of universal feature. So I'm coming to the end now. I hope I've given some kind of outlook of what is quantum turbulence, how it compares to ordinary turbulence. As you've seen that we see some similar feature, but also some differences. I want to propose a reconnection as a kind of somehow crucial mechanism in turbulence. We're still understanding what it does. And I know that at your institution, you're quite interested in neutron stars. Well, I've become interested in neutron stars. I've recently teamed up with people who do observations, and it seems, this is the result in a paper which we put together last year, that perhaps when we do some models, which are just models of neutron stars, I'm not so confident the models are good because we have very little, to test our models. But it seems that perhaps there are actually regimes of turbulence when there are glitches. So this phenomenon of quantum turbulence may actually be relevant also to understand neutron star glitches, besides also all sort of physics. At this point, I think it's time for me to stop, and I thank you for your attention.
Thank you very much indeed. Thanks. Wonderful talk. Hard to applaud in Zoom. There are people who might ask questions. Can you put your hand up in sequence, and I'll go to you for questions. I hope Professor Berenguer can take some questions. Dipankar, to begin with. Unmute. Yes, please ask you.
Thank you. I think this was an excellent and very, very interesting talk. Thank you for being so clear about what you presented. And I have a number of questions. I will ask a couple of them now. Maybe I'll get in touch with you for other more detailed ones. So one thing you mentioned when you introduced the vortices, that the core is of depleted density. So this is, of course, the superfluid density that we are talking about. Now, at the core, we would presumably have some amount of normal phase appearing instead of just being depleted.
Well, that's quite an interesting question. Right. From the point of view of the superfluid, I think this idea of zero density on the axis is possibly very close to physical reality for an atomic gas, because the Gross-Pitescu equation, which gives this prediction, is so powerful in the context of atomic gases. We see that it predicts everything. For liquid helium, I have my own doubts. Indeed, I know that there are people, in particular, somebody called Reatto in Milan, and others who have been working actually on making models of a vortex using more fundamental n-body quantum mechanics. So this is done essentially with the triangle function, and then you have to consider just typically of the order of 100 atoms and see which kind of vortex core and which energy you can put together. And reading their papers, I also understood that one has to be careful, because there is an approximation which people used to do in this context years ago, which actually produces a singularity on the vortex axis, and therefore total depletion on the vortex axis. But one can do better, essentially let the interactions between atoms to be switched on more, and then you get effects, including the rotons. Essentially, you see some kind of bound states of excitations near the core, and you see that the density is not zero inside the core, and on the core there is not a singularity, but rather some kind of classical Rankine vortex. Now, this is just theory. There is no experimental evidence of that, but it's really the most fundamental physics one can talk about for liquid helium. And I'm inclined to believe, and kind of I have a great respect for this work. It's quite interesting, and possibly that is the reality. We also know, and this is only pure superfluid. You asked about the thermal states and the thermal excitation, the normal fluid. Well, some years ago, I and Nick Prokakis in Newcastle did a simulation of an atomic condensate at final temperature using a model developed by Zaremba and Griffin, actually together with Zaremba himself. And essentially the model consists of a Gross-Pitescu equation which has been modified and coupled to a Boltzmann equation for the thermal excitations. So it becomes, frankly, a horrible problem, because the Boltzmann equation is quite difficult. However, the result of that, which was actually solved in the context of a single vortex inside a trapped gas of atoms, showed clearly that not only we have a formation of a thermal cloud of excited thermal states, but there is a concentration of thermal states in the vortex core. As the vortex moves inside the condensate, we see clearly that the condensate density goes to zero, as predicted by Gross-Pitescu near the vortex core, but the thermal atoms concentrate on the vortex core. So the vortex core becomes rich in thermal atoms. So I even thought that perhaps it does not really work that well. If you try to apply this as an experimental technique, the brightness of the vortex core can be even used to develop some kind of thermometry, because the thermal atoms collect in the vortex core. So the answer to your question is yes. I do think that actually there are thermal atoms in the vortex core.
Thank you. I think that was a very interesting answer. I have other questions, but I will wait until the others have finished their question, if there is time.
Okay, that's very generous. Let's move on to Kandu then next.
Hi, Carlo. Fantastic to hear all this stuff. I was wondering about these two types of turbulence that you talked about, the Kolmogorov and the other, Berlin or something, I guess. Do they coexist? For example, will the long vortices break up into loops, and then you have the other stuff decaying? I mean, do you have both k to the minus 5/3 and 1 over k? I thought you showed something.
Well, I'm not sure. I don't know for sure. There are some k. I think actually people have seen the decay of both turbulences, but not actually one necessarily turning into the other. So you have actually both kinds with the same total vortex length. It's really the way the eddies are organized. I do not know whether there is anything similar in ordinary turbulence, because I don't know enough of ordinary turbulence, frankly. Perhaps you can help me here. If I actually generated turbulence by essentially, you know, like, I don't know, if I put like, I don't know, like, you know, vitamin C kind of tablets, which are, you make bubbles, you know, in a glass of water, which I like to do every morning when glass of water with vitamin C, because it makes bubbles, it's kind of refreshing, whatever, besides being healthy. Well, actually, I'm exciting turbulence in very small length scales. So am I creating violent turbulence? I don't know. I don't know whether there is anything similar in a classical fluids. Perhaps there is.
Yeah, I mean, your pictures looked as if there were lots of loops in the Vernon turbulence, and there were lots of long vortices in other Kolmogorov turbulence.
We noticed that. So there is, in fact, in the numerics, we can actually, we find, you know, the distribution of kind of curvatures tend to be different.
Okay, I will have a look more and then get back to you. I think let others ask. Thank you.
Thanks, Nandu. We have Shubhadeep there next. Shubhadeep, go ahead.
Yeah, hi. Hi, Carlo. This is Shubhadeep. Very nice talk. So I have a question like when this vortice is formed, then there would be some energy associated to each of the vortices. That is the nucleation energy. And also, since there are finite number of bosons, I'm talking about BC, then there will be some mean field energy associated to the atoms in each of the vortices. So can you comment that how much, how they compare, how they scale, like the nucleation energy and the mean field energy of the vortices? And second associated thing is whether this mean field energy will actually make the vortices bigger in size, or actually they will help to collapse the vortices?
Well, at least in the context of Gross-Pitesky theory, you can decompose the total energy, which one can prove is constant, into various contributions. There is a contribution, you know, coming from which is essentially potential because you're trapping the system. There is some compressible kinetic energy, for example, which is the sound, and then there is an incompressible kinetic energy, which is actually the vortices. They flow around the phase defects. That I know for sure. And indeed, at the moment, we're tracking the amount of these contributions while simulating the turbulence experiments in Brazil. And it's quite difficult. I find it difficult to understand. I don't have a clear answer because in oscillating, in shaking the condensate, some of these contributions become dominant in different regimes, in different parts of the cycle. That is the thing which I know. Roughly speaking, the more vortices, the more energy, because when you have a straight vortex, you have simply energy per length, which is nothing but the tension of the vortices. So you would expect, in general, the more vortices, the more energy in the system. Although then, at some point, you have to take into account the orientation of the vortices, essentially the interaction between the vortices. So it depends whether the vortices are parallel or antiparallel, for example, or they are curved or not. It's quite, there is not a simple answer to that. It depends on the system.
Okay, thank you.
Thanks. Can we go back to Dipankar then?
Thank you. I'll ask one more question and then I'll let you go. So when you're describing this vortex field through this polarization of vortices, so you have some regions where the vortices are highly polarized, and then some regions where it is unpolarized. Now, overall, there is no angular momentum to the system, right? So these polarized regions must also alternate in polarization some way. There should be a distribution of that. Is that correct?
Yeah. First of all, I want to stress, it's a very mild effect. It took actually some time to track it numerically and discover it. It's some kind of partial polarization, which now actually we know how to pick up, but it's a small polarization of the vortices, which on the, if you just look, you would think they're just random. So it's partial. Then it is spontaneous. So you see these regions which are mildly polarized, which form, but then actually they break up, sort of they disassemble, and the polarization appears somewhere else. So they're not stable regions.
Okay.
It's a bit like the worms, which the so-called worms, which people observe in the numerical solution of Navier-Stokes. You see these intense regions of vorticity appearing, then they just drift about a bit, and then they vanish and they form somewhere else.
I see. So these are transient regions which just appear and disappear.
Well, no, at the end, actually, they're essentially, we know that Kolmogorov turbulence, what we call Kolmogorov turbulence, which contains this kind of partial polarization, can decay and remain, actually decay with the same predicted decay rate down to very small total lengths.
Okay.
So it can resist, during the decay, it will be less and less, but it remains so. So it does not happen that the polarization as such vanishes. The system actually loses energy and length, but the partial polarization as a fraction of the total seem to remain.
I see.
So
okay.
The details of this mechanism, I do not know. Lots of things I don't understand.
Thank you. Thank you. It's an excellent discussion and excellent talk. Thank you very much.
Thanks very much indeed. It was a fantastic event. I mean, the talk and the questions and answers, we could go on forever, but let's please applaud and express our gratitude to Professor Berengi. This was excellent. I hope to see you soon here, when travel becomes possible. Please come and
sometimes reality rather than Zoom.
Thank you, Carlo.
Exactly. Thank you very much.
Goodbye.
Bye.
Thank you.
Bye.